Here we are using a table approach to test for system consistency, and we have the two propositional variables, P and Q, and then the three uh, specifications were represented by P or Q, P implies Q, and the negation of P. And if we have a consistent specification, there will be at least one row where all are true, all of the specifications are true for some truth values of P and Q. So let's go ahead and fill the table out. P or Q gives us true, true, false. Oops, that's not correct. True, 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 false. P implies Q gives us true, false, true, true. So for the first two specifications, there's two ways they can be consistent. For the first line, both are true. P is true and Q is true. And in the third line, when P is false and Q is true, both lines are true. Now let's add the third specification, the negation of P, so we get false, false, true, true. So we lose the first line as an option for consistency, but the third line still has all true values. So for the three propositions, we have a consistent specification if P is false and Q is true. If we end up adding the negation of Q as a specification, we get false, true, false, true, then we do not have a consistent specification because there is no row for which all of the specifications are true. Let's look at the knight and knave problem. Here we can use a truth table to look for if we can find a solution to determine whether A is a knight or B is a knight. Now in this case, if we're trying to say for sure if A is a knight or a knave and B is a knight or a knave, there can be only one row that has all truths. Otherwise, we won't be able to tell. So what are the possibilities? Well, we'll just say that A is a knight, and that's either true or false, and B is a knight, and that is either true or false. And there's four total possibilities for those two propositions. And then the puzzle is A can A say that B is a knight, and can B say that we are opposite? And those both need to be true to solve the puzzle. Let's work through A. Can A say that B is a knight? Well, can A say that B is a knight? And the first one, yeah, because knights always tell the truth and B is a knight. So yes, A can say B is a knight. For the second line, can A say that B is a knight? No, because A is a knight always tells the truth and B is a knave, so he cannot say that B is a knight. In the third line, A is a knave and B is a knight. A can't say that B is a knight because that would be a knave telling the truth, and so that's false. And can the bottom line, if they're both knaves, can A say that B is a knight? Yes, because B is not a knight, and A being a knave will lie about it, so yes. All right, so there's two possible answers. They're both knights or both knaves. Now let's look at the second part of the puzzle. Can B say that we are opposite? Well, if B is a knight and A is a knight, they're the same. B and knight, B can't tell a lie, so he can't say that we're opposite. If B is a knave and A is a knight, they are opposites. That's the truth. B can't tell the truth, and so he can't say that they are opposites. If B is a knight and A is a knave, can B say that we're opposites? Yes, because they are opposites, and B would be telling the truth. And if they're both knaves, can B say that we're opposites? Yes, because they're not opposites, and B would lie since he's a knave, so he could say that they're opposites. So the only um, line for which both of those statements can be true is when